Okay, welcome back, everybody. Hope you had a great lunch. We will now continue the day with Bernd Sturmfels, who will tell us about minimal kinematics on M0N.
Yeah, well, thank you very, very much. So I'd like to present this paper with Nick Early, who is a postdoc in Leipzig, and Anael Pfister, who is a beginning grad student, PhD student. So in particular, I have to tell you what's M0N. Here's a picture for n equals 5. And I'll have to tell you what's minimal kinematics. That's the goal. Now, M0N is the moduli space of n distinct points on the line, or the Riemann sphere over the complex numbers. One way to define it rigorously is you take the Grassmannian of GR2n of two planes in n-dimensional space. You restrict to the locus where all the Plücker coordinates are non-zero, and then you divide by the torus action. So in elementary terms, points in this space can be represented by 2 by n matrices of this particular form. So the columns are points in the projective line with two homogeneous coordinates. And I can always, without loss of generality, I can fix 3 of the points, the first one, second column, and the last column. And then I have parameters x1, x2, up to xn minus 3 left. So, and we want these points to be distinct. This means that the 2 by 2 minors of this matrix, the 2 by 2 subdeterminants, are non-zero. So the choice of such a matrix is called gauge fixing by my physics friends. So this space is a very affine variety, open variety of dimension n minus 3, the number of parameters. And as I said here in this definition, the Pij are non-zero. Now this very affine variety is the complement of everybody's favorite free hyperplane arrangement, right? So we've heard in the previous talk that the reflection arrangement given by the n-choose 2 hyperplanes xi equals xj is everybody's favorite, and we're going to talk about other graphic arrangements today. So here's the picture for n equals 5. So for n equals 5, this is a 2-dimensional surface. So it's given by the complement of these 6 black lines in the real projective plane. Now you think what you see are 12 triangles in the complement, but actually they're 12 pentagons, right? Because the right thing to do is to blow up these intersection points. If you blow up these intersection points, that is to say, you replace each of these points by a real projective line, also known as the circle, then what you see are 12 pentagons. So the real surface, M05, really consists of 12 open pentagons, and in the compactification, they are closed pentagons. So let's look at the same picture in 1 dimension higher for n equals 6. So M06 is a surface, is a threefold. And here's the same picture taken from Satyan Devados. So the threefold M06, so again, this is the space of 6 labeled points on the line, is the complement of the 10 planes in 3 space, the planes xi equals xj. And then this complement is the union of 60 open associahedra. So associahedra were also mentioned in the first talk this morning. They have 14, that is to say Catalan many vertices. So you get this very nice space glued from 60 3-dimensional associahedra. So quick reminder, right? So the associahedron, this 3-dimensional associahedron is a 3-dimensional simple polytope with 14 vertices, 21 edges, and 9 facets. And the vertices correspond to the triangulations of a hexagon in the plane. And as I said, 14 is the Catalan number, and of course related to the Tempel-Lieb algebra and many, many things. Okay? So the combinatorics of M0N, has these associahedra. And this is a very, very beautiful space. And I would like to tell you now next what's minimal kinematics. And please interrupt me. So if there are any questions about for me, please interrupt me. And like in the calculus class, right? So if you don't have questions for me, I'll have questions for you. People in the first row will never get asked questions, but of course, people in the back will be in trouble. Okay, everything clear? M0n. So Julia isn't going to be even second to last row. Julia will definitely be asked the question. Okay, now what I'm up to. This is the logo of a school I'm attending in 10 days in Princeton. So I am studying particle physics right now. So I sold my soul to the particle physicists. Now what do physicists do? They're interested in integrals. In particular, here's a famous integral from the 1970s. It's called the Koba-Nielsen string integral. And well, first of all, what are we integrating over? So the cycle we're integrating over is one of our icosahedra. So we take the positive region of M0n. This is one of these 12 connected components. Then there's a scaling factor, epsilon. A little later, epsilon will go to 0. Epsilon to the power is the dimension of our moduli space. Then there's the Park-Taylor integrand, right? So this is the reciprocal of P12 times P23 times cyclically around, right? Until you loop around, right? Lx is already thinking about positroids, so you multiply cyclic Plücker coordinates. And then there's a Plücker monomial, an arbitrary Plücker monomial in the Pij's to some power Sij. I'll tell you what those are, raised to a further power of epsilon. And then this is supposed to be, you integrate out all the coordinates, the p's, the moduli coordinates, and what's left is some kind of a function of these Sij's. Now these SI states are called Mandelstam invariants, and they encode kinematic data of a scattering process. So in Europe, we have this thing called CERN. It's very expensive. We pay a lot of taxes so that under Switzerland, they can shoot these things around very fast. They collide, and then these Sij are kinematic data of such a collider experiment. Now, what do they satisfy? They satisfy the Sij. They form a symmetric matrix. Sij is 0. And then there's a condition called momentum conservation, which says the row sums of this symmetric matrix are all 0. Those are going to be the hypotheses. Yes, question? They're parameters. Let's say they're real parameters. They could be complex, but let's say they're real parameters. Timo? Yeah. So those are parameters. Not necessarily integers. Yeah, it's a kind of period integral, exactly. So, okay. Very good. Now we're going to say, we're going to set epsilon goes to 0, right? So this is a highly transcendental function. It's a very, very complicated transcendental function. But the limit as epsilon goes to 0 turns out to be a nice rational function. It's the leading singularity. And it's a rational function of degree 3 minus n. So minus the dimension of the moduli space. And it's actually a very, very beautiful rational function. So in our n equals 6 example, it looks like this. So it has a name. It's called the Biot-joint scalar amplitude and phi cube theory. Never mind what are these words. But this is it. So it's a sum of 14 terms, right? So these are, it's a function, a rational function, homogeneous of degree minus 3. And it's the sum of reciprocal products of linear forms. So the Sij, you know already what they are. So if you have 3 indices, so Sijk means Sij plus Sik plus Sjk. You just add up all 3, right? Okay, now of course this is understood modulo momentum conservation, right? This is not a unique formula. Yes, Frank?
So there are 14 vertices in your icosahedra.
Exactly.
These
Yes.
sums of vertex points.
Yes, these are exactly.
Is this the Brion formula?
No, it's related to Brion, but it's not the same. So this is really, yeah, so you're summing over the vertices here, and these are basically, has to do with the interior edges. So basically the combinatorics of the icosahedron drives this formula. Okay, so there are Catalan many, I'm sorry, I'm boring people with Catalan numbers, so there are Catalan many terms in this expansion of the Biot-joint scalar amplitude. Now, Bernd studies physics, but he likes statistics, right? So the corner back there, you know, I have to study physics, but I actually like statistics. So let's look at the so-called CHY scattering potential. So that is the logarithm of the expression that I'm integrating. Right? So you take this expression here. For Piotr, it already looks like a Bayesian integral. So I take the logarithm of this thing without the epsilon. And then this is this logarithm. And CHY is the name of a theory. So the CHY scattering potential is this associated log likelihood function. Okay? Now it turns out that this function is actually well defined on M0n. Right? So it looks like a function in Plücker coordinates, but I define the moduli space as the Grassmannian modulo the torus action. And it turns out that momentum conservation, the the linear equations for momentum conservation, they exactly guarantee that this is well defined on the orbits in the quotient. Right? So another way to say this, momentum conservation says I can rewrite this in terms of cross ratios. Right? So cross ratio would be P12 times P34 divided by P13 times P24. Right? And that ensures this. Okay? Now, yes, question.
I'll just yell. Pij is pi minus pj?
No, pi, yeah, it's xi minus xj. So pij at the beginning are simply the 2 by 2 minors of this matrix. And in a moment, just to keep it simple, I'm going to fix this gauge fixing. So I'm going to work with this particular matrix. So therefore, every pij is a function in the x's. Okay, so typical Pij will be xi minus xj, but some special ones will be 1. So for example, P12 is 1, and the logarithm of 1 is 0. Okay, also, the first and the last, so there's several of them that are 1, and those we're going to drop out in a moment because the logarithm of a constant here is just 0. Okay, so by gauge fixing, we only look at those Pijs that are actually, non-constant function of the xi's. So we only have to look at these indices, column pairs ij. We're not using the last column n, and also not using the pair 1, 2. Okay. So now for the third to last row. So in statistics, the Sij represent the data, and we'd like them to be non-negative integers, right? And then the scattering potential is known as the log likelihood function. Right? Now, I don't think Hal is here anymore because he has to speak to some other physicists. But the log likelihood function, in particular, the likelihood correspondence that Jose will talk about later this week, is really the same thing as the module of log differentials. Right? So you really think about this, the sheaf of log differentials that Hal spoke about this morning. You'll see a version of this again in the likelihood correspondence of Jose's talk. Now here's a proposition. In this case, it's very easy, right? So if the Sij are general, and in fact they can be positive real also, integer also, then the log likelihood function has n minus 3 factorial complex critical points, so dimension of moduli space factorial many critical points. And if the Sij are real, then all the critical points are real. This is sometimes known as Varchenko's theorem. So if you have the log likelihood, the likelihood function, or master function on a hyperplane arrangement, then for real data, all the critical points will be real. Okay, this is the setting. The setting is we have this, and we have that. Now how is the Koba-Nielsen integral related to these critical points? Well, this is the CHY formula, and I'm first in green, I'm going to say it in words, and then I'm going to state the formula. So in words, we're going to square the Park-Taylor integrand. We divide by the Hessian of the function we're optimizing, and then we're summing over all critical points. Okay? So this is the sum. Now here this minus has to do, right, so in statistics we're doing maximum likelihood, we're maximizing likelihood function. In physics we're minimizing the potential. It's just off by a sign. Then here we're summing over all critical points. So p hat is the sum of all critical points. And here we have a nice rational function, also I squared. So I was the Park-Taylor factor. And then the Hessian of the likelihood function, this is you take the determinant of the matrix of second derivatives. It's another rational function. You plug in every critical point and you add them up. Okay? Now that is going to be a rational function in the Sij. So now if the Sij are parameters, then by Galois theory or something like this, right, this will be a rational function in the Sij. Now trouble is the number of summands is very large, and this rational function is exactly our rational function. Right? So if the theorem says that this rational function here is exactly the one that you obtain by summing over all the critical points. Okay. Now what do? If you have a polynomial system with very, very, very many solutions, right? Now our natural tendency is we're going to write a grand proposal that says from now on we're going to study even larger systems and we're going to develop tools for finding them all and controlling them all. Right? That's one approach. Well, another approach is to just replace the polynomial system by another polynomial system that has only one solution. That's what I'm going to do now. I'm going to say, this is too many solutions for me. I'm going to instead look at a polynomial system that has only one solution. Might as well, right? And this is called minimal kinematics. So this is a reference to this paper by Cajazzo. He's in Waterloo at the Perimeter Institute, a quite distinguished physicist down the road. And this is the basic reference on minimal kinematics. And of course, this is the positive tropical variety of the Grassmann. Okay. So this is minimal kinematics. So let me define this formally. So well, first let me give you the theorem, and then I'm going to explain the words in the theorem. Okay, so the theorem here, the first theorem today, is the choices of minimal kinematics on our moduli space are in bijection with certain graphs, and these are called two trees. So two trees is a certain very special class of graphs on n-1 vertices. Okay, so what I need to do now, I need to define the red term, minimal kinematics, and I need to define the blue term, two trees. Okay, so here are the definitions. So I'm going to fix any subset T of the set S. So S were the relevant pairs, the relevant hyperplanes in the reflection arrangement. I take any subset T, and I'm going to restrict the log likelihood function restricted to those Sijs. Okay, so I'm setting some Sijs, Jose, to 0. An operation that Jose really likes, right? And T is the ones that are left. They're still parameters, right? Now I'm going to say that this subset T exhibits minimal kinematics if this new likelihood function has exactly one critical point. And it's inclusion maximal with this property, right? So I'm progressively setting Sijs to 0, right? The number of critical points goes down, right? And then when I hit 1 for the first time, then I'm going to say what's left I call minimal kinematics. Okay. Now, since there's only one critical point, now the coordinates of that critical points will be a rational function in S. So if you have a polynomial system that depends, polynomially on parameters, if it has only one solution, then that solution will be rational in the parameters. So those are the rational functions I'm going to be interested in. Now the second blue definition is two trees. So this is a class of graphs. So these graphs are not trees. They're going to be not trees. And it's going to be inductive. So if I have two vertices only, right? So in this notation that would be n equals 3. Then a single edge. So a single edge with two vertices, that I'm going to call a two tree. Okay? And then what I do, I can get any two tree on the first k positive integers by taking any two tree on one fewer vertices and throwing in two new edges, namely, I pick any edge ij of the small two tree, and I throw in the two new edges ik and jk. So it's clear, you have a small graph, pick an edge, and then connect the new vertex with the two endpoints of the edge you picked. The world's simplest definition. Question? No, I keep ij. So I just inductively, so any graph I get this way, I'm going to call a two tree. Okay, so let's do some examples. So So first of all, every 2 tree, the way I set this up, they're going to have n minus 1 vertices, and I'm going to delete the initial 1t. So for technical reason, when I do the counting, I only count the even number of new edges. So beginning there's 1 edge, then I add 2, I add 2, I add 2, and so there's going to be an even number of edges I added. So altogether, every 2 tree has 2n minus 6 edges. Now, if with the labeling, right, the number of 2 trees, labeled 2 trees in this labeling is the double factorial, 2n minus 5 double factorial. That's because you have an odd number of choices at each stage, right? So it's the double factorial is 1 times 2, 3 times 5 times 7 up to 2n minus 5, okay? Now, with symmetry, if you mod out by symmetry, then the number of 2 trees goes like this. So if for n is 4, 5, 6, and so on, it grows like this, 1, 1, 2, 5, 12, 39. So then you go to the, this is explained on the online encyclopedia of integer sequences, and there you find a big discussion of 2 trees and 3 trees and things like that. Okay? These are the 2 trees. Okay? Now in particular, if n is 5, right, then there are 2 non-isomorphic 2 trees, and I have visualized them here in these yellow pictures. Now, in these 2 trees, they're sort of canonical triangles, right? Because each time I had an old edge and I glue in 2 new edges, and I sort of think about this as a yellow triangle. So let's look at this one. So here, I'm starting with 1, 2. This 6th is a dummy. This is sort of, this is 1 edge with the 6. I'm going to keep this as a dummy, really, so the graph is down here. So first 3 gets connected to 1 and 2. Then I pick an edge, for example, 1, 3, I hook up 4, then I pick 1, 4, and I hook up 5. Right? So this is a planar 2 tree. This is a 2 tree that I can draw in the plane. Okay? Then there's another one that's not planar, so it starts out just the same way. So I start out with 1, 2, I connect with 3, then 4 connects to now to 2, 3, and 5 also connects to 2, 3. So this 2, 3 has 3 triangles adjacent to it. So this is a non-planar 2 tree. So these are 2 trees for n equals 6. And remember, this was our moduli space glued from 12 pentagons. Okay, so now the theorem. So it's clear now. So I've defined what minimal kinematics means, and I've defined what 2 trees mean. So I claim the subarrangement, the graphic arrangement of these 2 trees has exactly 1 critical point, 1 bounded region. Now, what is the critical point? Well, let me give you the coordinates, right? So there are these 2 examples. There's the first tree, yes.
What if you always choose the edge 1, 2 to glue with this tree?
Yeah, that's allowed.
But you
Seems
get something
different.
Let's see.
This has like a...
No, you get the same. So this one is a dummy. This is kind of this is a dummy, right? So this is actually the one, yeah. So this one, so for technical, it's a graph on n minus 1 vertices. For later purposes, I'm always going to take the starting edge with the extra last column here. I'm going to put this in at the end, right? So we're going to get to some really cool Tevelev stuff at the end. Okay, very good. Thanks for paying attention. And now here are the critical points. So for example, for this one, right, so you calculate it, right? So here is the unique critical point. So P1, 3, this is the estimates. This is the unique critical point written as a rational function. So these are, of course, scale invariant. So they're homogeneous rational functions of degree 0. And the first one, these are the 6 relevant coordinates for the critical point here. And then down here, you have the 6 relevant coordinates for the critical point down there. Okay. Now, what do you notice? Well, what you notice is that each numerator and each denominator is a product of linear forms. Right? That's a miracle, right? Because polynomials and several variants, they don't factor, right? There's no. The second miracle, it's not just linear forms. These are positive linear forms. So these are linear forms, all of whose coefficients are positive. In this case, they happen to be all 1. Okay? So every coordinate of every critical point is an alternating product of positive linear forms. in this example. Yes, Jake?
Remember that coefficients other than 1?
Yes, not in this, so in general for statistical models, yes. Here I'm going to give a formula, you only get 1. In this context, you only get +1. Okay, now,
So alternating means you have like an order of them?
no, alternating means, so alternating product, I just mean product in the numerator
Okay.
divided by a product in the denominator. Right, so yeah, by alternating product, it's a Laurent monomial of degree 0 in these linear forms. Good. Yeah, thanks for asking so many questions. I think we're doing great in time. 12 and 25.
Those are always famous last words in talk.
Well, let's see how it goes. Okay. Now let's go back for a moment to our bi-adjoint scalar amplitude. Now this looks deceptively simple. This looks very, very simple, right? But if you take this rational function and you're interested in the variety it defines, if you clear denominators, then the numerator has like 300 terms, right? It's not only a very big numerator, right? It's also not unique, right? Modulo because we have momentum conservation, right? So this is really a very, very deceptively simple expression. Now let's look at this one. So here we're setting in this 2 tree, so the non-edges are 2, 4 is a non-edge, 2, 5 is a non-edge, and 3, 5 is a non-edge. So if we set those expressions to 0, then the resulting specialized amplitude is again a rational function of the same kind, right? It's of degree 0 and numerator and denominator factor in the prescribed way. So everything inside is a product of positive linear forms. Right? So
That doesn't equal 0. That means some of the 3 indices is just 2.
yes, for example, so
Straight hole.
exactly. So it sort of does, but you have to work modulo momentum conservation.
Okay.
So that you're actually working on this codimension n linear space. You have to be a little bit careful. You know? Now I have to say, these physicists, they're incredible with residues. I mean, they know how to compute residues. Yes, Timo? Okay, I'm setting these 3, I take this rational function, yeah? So this is a rational function in the Sij's, but I restrict it to the codimension 6 linear space given my momentum relation. And afterwards, I'm setting these 3 blue coordinates to 0. Then after the specialization, this function becomes this function. This is homogeneous of degree -3. Right? You have a cubic in the numerator, you have a sextic in the denominator, so I'm saying this equals that after you specialize to minus. So rather than working with 6 critical points, 6 being a very, very large number, I now have only 1 critical point. And that gives me this specialized amplitude. Okay. Now, of course, what do mathematicians do other than hanging out with physicists? Well, we like proofs, right? So this is my goal, actually. So when people ask me, why am I now with I love doing cool math, you know, but, you know, it's so bothersome I always have to write proofs. So, you know, I'm going to write some cool math papers with the physics. Okay. Anyway, so I'm still a mathematician. So here's an excerpt of the proof, one direction of this theorem, and you can see many of the combinatorics words that people like, right? So there's a hyperplane arrangement, there's Slavsky's theorem for counting regions, right? There's a beta invariant, and then it has to do with series parallel graphs. So these 2 trees are the maximal, so there's a notion of series parallel matroids, and they're all graphic, and then the maximal series parallel graphs happen to be the 2 trees. That's roughly the story. And that's one direction of the proof. And the other direction of the proof is the supersolvable fibration that kindly was mentioned in the first talk. That fixes the Euler characteristic. Okay, we are doing great in the time. Now, mathematicians like proofs, but also mathematicians like other mathematicians. Now here up in the title of the slide are 2 mathematicians I happen to like. So that's Misha Kapranov. I like others too, but in particular I like these 2. So I like Misha Kapranov and I like Juni He. And here's a theorem which I will attribute to Kapranov and He. And let me first state the theorem and then maybe say a word about the history. So now let X be any very affine variety. So a very affine variety is a closed subvariety of an algebraic torus. So I take a complex algebraic torus, and then closed subvariety, this is the zero set of a system of Laurent polynomial equations. Okay? Now for any such variety X, the following three conditions are equivalent. First condition, X has signed Euler characteristic 1. Right? So the Euler characteristic of this, so it's a complex manifold, it's a real manifold with twice the dimension, and the first condition is Euler characteristic is either +1 or -1. Okay? And this, in our case, counts the number of critical points. I should have said that. Right? So the number of critical points is the Euler characteristic, and the sign of the Euler characteristic, and this is 1. Okay? Now, second condition is the log likelihood function on X has unique critical point p hat. Now, it turns out the log likelihood function or scattering potential or master function, makes sense for any very affine variety. You simply take, the logarithm of some multipliers. So you take some coefficients and then log of the defining coordinates of the torus. Right? Now 1 and 2 is easy, but the third one here is where the meat is. Right? So the third condition is that X admits a very particular rational parametrization, and this was called the Horn uniformization. So Kapranov studied this topic in the early 90s, published a paper in 91, and this is a very particular parametrization, which I will explain. I will explain this formula. Okay? Now, who is Horn? Horn is not the one that you think of when you think about Knudsen and Tau. Horn was a professor in Germany in the 1870s, and he studied ordinary differential equations. He was actually in Darmstadt, my alma mater, and he taught ordinary differential equations, such as hypergeometric differential equations. And this was picked up by Kapranov, and he called this the Horn uniformization. So what does this say? So this says that the critical point p hat is given by an explicit formula in terms of the parameter S. And here's what we do. We take H as an integer matrix with m columns, and m is the number of ambient coordinates. Lambda is some integer vector with m coordinates, and j gets ±1 in our application. Every coordinate will be ±1. And this pair of the matrix and lambda, we're going to call a Horn pair, and it's an invariant of the variety. Right? Now, what does this mean? Okay, so S is a column vector whose entries are unknowns, the S's. Right? So S is a column vector of unknowns. H is a matrix. Okay? Now, therefore, H times S is a column vector of linear forms. Okay? So here I have a column vector, okay, raised to a matrix. Now, what does that mean? Well, a vector raised to a vector, you know what that's a scalar. Right? So if I have a vector of length 3, ABC, raised to a vector of length 3, UVW, right, then it's A to the U times B to the V. Okay, so we all know vector raised to vector, and vector raised to matrix is you do this column-wise, and that's a vector. Okay, so therefore this is a vector, right, whose entries. This is now a alternating product of linear forms. Okay, and this star is the Hadamard product or coordinate-wise product. So I multiply the ith coordinate of this vector with the ith coordinate there. Very concise notation. Now this, of course, is very interesting in statistics. So He sort of proved the equivalence in this form. Junior He proved this in a complex setting, and we then redid this. So we further developed this in the case that was actually interested in statistics over the real number. So we turned this into a real algebraic geometry theorem in this paper with Duarte and Mariglioni and Mariano. And we also sort of introduced this Horn pair notation in this journal, in this paper in Bernoulli.
So this isn't just a point P, this is the whole variety X.
This is a parametrization of X. Right? So as a, exactly. So I'm varying over all data, over all Mandelstam invariants, and this parameterizes the variety. It's a rational parametrization, so uniformization here stands for parameterization. So in our application, M is 2n minus 6 the number of relevant edges of the tree, and S is the column vector of Mandel-Stamm invariance. Okay, so this formula here is precisely this formula. Okay, that's why this slide is called Toard's horn. Right? So this is the structure in this, and so if you unravel the structure here, it's this concise formula. Okay, so this is the Kapranov-Herr theorem, and algebraic statisticians by now know this quite well, but in the particle physics community, they hadn't seen this before. Okay? Now here is, just to make this very precise, so here are the horn matrices for our two examples. So there's the planar example. So these are, highly structured 0-1 matrices where the columns sum to 0. Right? The columns have to sum to 0 because we're getting, in the end, rational functions homogeneous of degree 0. Right? And then here's the other one. So if you take these expressions, you plug in here, then you get these formulas. Okay. Now there's also, here's yet another way of paraphrasing the same thing, and this shows that all the coefficients are +1. So let me state a corollary, and this is again equivalent to in our case. So let me write bracket Sij for the sum of all Mandel-Stamm invariants SLM, where the edge LM is a descendant of the edge Ij. So let's remember how these two trees were built, right? So every edge sort of spawns two new edges. So therefore, edges have descendants, right? So they're not, so in this two tree, some edges are descendants of other, there's children and so on, and then, grandchildren and descendants. So I'm summing over all descendants, and that's the bracket notation. And then, so you can also then write it the following. So the coordinates of the unique critical points, so the LM coordinate is the product over these simple rational functions, bracket Sik divided by Sik plus Sjk, and the product runs over all ancestral triangles, Ijk, of the edge Lm. So Lm is an edge further down in the two tree, but it came from some edge, but that edge was participating in a triangle. And on such a triangle, I'm going to call it an ancestral triangle. So you multiply here over all ancestral triangle, and this is okay, down here is the definition. So descendant refers to the transitive closure of the parent-child relation in constructing T, and then, okay, Ijk is an ancestral triangle. If there's an order to this, so Lm has to be descendant of Ik. Okay, so this is the unique critical point. Now, what are we going to do with this? So now what we're going to do with this, we're going to actually, I'm going to do great in time. Right? We have still 12 minutes and 18 seconds left. So, so we're going to go back to the amplitude. So let me give you a formula for the amplitude. And I'm going to first state the theorem, and then I'm going to slowly develop the definition. Okay? So for every two tree, I now have an amplitude, and it simply has this simple formula. So I'm going to reverse now. I'm going to again take the product over all triangles, now Ijk, and the numerator I have the sum Sik bracket plus Sjk, and then the product of the two things. So it looks like this one, but it's sort of flipped, right? The sum goes up in the numerator. And you can see this is a homogeneous rational function of degree 3 minus n. Do the counting, right? So there are the n minus 3 triangles in our tree, and then this has degree 3 minus n, as it should, right, for these amplitudes. And in green, again, the words, so this is a product of n minus 3 linear forms in our column vector Hs, H is the horn matrix, divided by the product of the other two n6 minus 6 linear forms, again in the same Hs. So the total number of linear forms in the picture is a 3n minus 9, and they all have coefficients +1. Okay? Now, if the two tree happens to be planar, then this is precisely the restriction of the earlier biojoint scalar amplitude to that tree. Right? So what I'm saying here in the corollary is that this specialization works whenever the two tree is planar, but now we have a more general notion of amplitude when the two tree is not planar. Okay? So now what I'm going to slowly go over the definition. So for physicists, these amplitudes are leading singularities of the amplitudes they're actually interested in. So it wasn't a stupid thing to do to replace the n minus 3 factorial criticons by only one, because this gives a very good control over the degenerations of the amplitude they're interested in. So they're leading rational functions of some big, sort of unknown rational function. Okay, so to go over some juicy definitions, let me define the matrix of circuits. Yes, matroids. Everybody and their sister loves matroids. So let's look at the following n minus 2 times n matrix. What I'm going to do, the rows are indexed by triangles, ijk, yellow triangles. I'm going to write down this row vector. So I'm going to write pjk times ei, ei is the ith unit vector, minus pikej plus pijek. So for example, here in this matrix, there are 4. Now I'm using the dummy triangle for the first time. So I'm using all 4 triangles. And the first row, I have P23 in the first column, minus P13 in the second column, P12 in the third column, and yes, that's Cramer's rule. Okay? And similar for the others. Now, because that's Cramer's rule, the rows, the 4 rows of this matrix span the kernel of the 2 by n matrix we started out with, right? So 42 minutes ago, we started out with the 2-rowed matrix X, and this is a distinguished choice of kernel generators. Okay? Now, because that is so, it turns out the maximal minors of this co-circuit matrix, well, the minor that you get by deleting column I and column J is up to sign Pij times some global delta, and this global delta is a polynomial, and it's the GCD. It's the greatest common divisor of all the maximal minors. Okay, and this is going to be very interesting. Now, in our case, this turns out as a formula. So the GCD of the maximal minors, in this case, is going to be a Plücker monomial, Pij, raised to some exponent, and the exponent, ij exponent, is the number of triangles containing a given edge, and this is a monomial of degree n minus 3. So we're going to see this dimension of the moduli space again and again. Okay, that's the matrix of circuits. And then here's the definition of the amplitude, right? So we're defining the integrand for a given 2 tree to be the square of this delta divided by the product over all Pij, Pik, Pjk over all triangles. And then that's this expression with the same thing minus 2. So it's a rational function of degree n minus 1 in Plücker coordinates. And then the amplitude is defined just like in the earlier CHY formula. Namely, it's the integrand squared divided by the Hessian evaluated at the unique critical point. So now we don't have to sum over critical points, but we only just evaluate at the one critical point. So same localization formula, but only at one critical point. So for this one, we get this. And so with this definition, then this becomes a theorem. Okay, now what I like to do in the last 3-4 slides, I'm going to shift gears now. So now I'm going to talk about a different notion of tree. I'm going to now replace the 2 trees by something that sounds very similar, but is fundamentally different. And those are the so-called hypertrees. So these hypertrees, they were invented by Kostrave and Tevelev. And so they had 2-3 articles in starting about 10 years ago. And this was a major, major contribution to the birational geometry of M0n. It was a big open problem, Fulton's conjecture after Frank's advisor. And people are very, very interested in what about the cone of divisors? Is it polyhedral? Is it not polyhedral? And they solved this. And they solved this using a combinatorial gadget called hypertrees. So what are they? So hypertree is a collection of triples. Namely, you take n minus 2 triples in the ground set 1 up to n. And there are two conditions. The first condition is that each index I should be in at least 2 triples. And then there's sort of a spread out condition, right? So for every subset of these triples, their union, the size of their union should be large enough, right? So you have this hypergraph, and you want this hypergraph to be sort of spread out. The first one says every vertex participates. The second one says it's spread out enough, right? Now what about these hypertrees? Well, they have the same number of triples as 2 trees, and the matrix MT, and the integrand IT, and the amplitude little mt, they're all defined exactly as before, right? So the same definition as before. The only difference is 2 trees are not hypertrees, right? And that's because of this second condition, because the 2 trees are not spread out enough. They tend to cluster, right? They have like leaves, and so they're not spread out. Okay, so what about these hypertrees? Well, let's do an example. So here's an example of something they call an irreducible hypertree. That's, for example, if you take those 4 triangles, every other triangle in the boundary of an octahedron. It's an irreducible hypertree. And then there's the corresponding circuit matrix as before. You take the GCD of the 4x4 minors, and you get this irreducible polynomial, P12 times P35, and then minus this one. So this is an irreducible degree hypersurface in the Grassmannian and also an M06, so it's projectively invariant. It's projectively invariant because each index occurs the same number of times. Each index occurs exactly once, so this defines an irreducible hypersurface in our threefold, which was defined by gluing 60 associahedra. Right? Now, these hypertrees were also independently invented by the physicists. They call them on-shell diagrams. And so here are 2 references. So there's a literature now on non-planar on-shell diagrams. They also call this non-planar Playbig graphs. Right? So our friends in MIT combinatorics, they love Playbig graphs. But Playbig is like planar, bicolored graphs, right? But for the physicists, it's too special. They don't want planarity anymore for the same reason that we went away from planarity. So they are sort of this literature on non-planar Playbig graphs, and this is one of the early papers on this. Now, Genya Tevelev published an amazing paper early this year called Scattering Amplitudes of Stable Curves, and he in fact proves the equivalence. So at the very end, the last section, he shows that this definition of hypertrees that he had with Tevelev, with Castreve, is the same as the non-planar, the on-shell diagrams that the physicists have. But now we can do divisors. Now we can do we have amplitudes, right, for this. So for example, in this example, now this is not a 2 tree, so therefore there is more than 1 critical point. In this example, there are 2 critical points, right? The scattering potential or log likelihood function now has 2 critical points. Now, if you sum over the critical points, you get the sum of these rational functions, of these, they're the polytope with, I think, 20 vertices. I get this right? That's 20, or did I count? No, 8 plus 6. That's also, I'm sorry, it's 14. It's a rhombic dodecahedron, right? So the role of the associahedron for this example is played by the rhombic dodecahedron. And so there is this theory, but now we have more than 1 critical point. So with 1 minute and 17 seconds to go, let me close on some open problems. So what did we do? Well, we talked about the Grassmannian 2n, which led us to the moduli space M0n, and we talked about 2 trees. Now this situation we generalized to hypertrees. Another natural generalization is to go from the 2n Grassmannian to arbitrary Grassmannian, since everything is wide open. So here are a couple of questions. Find a formula for the ML degree of any hypertree. how is this ML degree related to the geometry of the hypertree divisors? So the hypertree divisors, they were the heroes in the Kastraveh-Tevelev story where they advanced the birational geometry. For larger K, how can you reach ML degree 1? By restricting, to other subspaces. And then, of course, M0n in general, we have this moduli space of n labeled points in projective K-1 space. And it would be very interesting to study this and to develop this more generally. So the conclusion is that the physics of scattering amplitudes inspires the combinatorics of M0n. All I left to say, happy birthday, Frank.
Questions for Bernd?
Sorry, I did never ask you a question, Julia. I can ask you later, okay?
Yeah, so one of your extensions, the previous page, the second one, going to GRKN, that people really suck on that, aren't they? I mean, the combinatorics.
Yes. Now, of course, we know, that we can never hope for very general statements, right? I mean, things are universal and so on, but how about 3.6, 3.7? Okay. I mean, the cluster people are chugging along as well, right? So we'll let's start slowly. I think Elizabeth has a question. Oh, yes.
Thank you. So when you set the SIJs to 0 in the original sort of formulation with the two trees, like was there sort of a pattern to the ones that you had to set to 0 to get down to the
Yes,
minimal?
yes. The pattern is the two tree.
Oh, it's the two tree.
The two tree. So the non-edges of the two tree those are the set to 0.
Okay.
Yeah,
And
so
then
that's
when you go to the hyper trees, is there?
Well, for the hypertree, it's not a two tree, right? There's going to be
Yeah.
higher ML. There will be a higher ML degree, and we don't understand in general. But it would be very nice to relate it to these hypertree divisors. So
Okay, or like some. Okay, but no intuition.
we don't know yet. So that's why, yeah. So these are, and we got as far as we could in this paper, and then we left this for future smart people. Yes, there's a question back there. Kisun?
So for the ML degree, is one just special, or like if you assume like ML degree 2, can we just expect some other like characterization?
You asked about the representation for ML degree?
ML degree, like why one is so special?
Why is one special? Well, one is very special because you have a rational formula, right? You have a polynomial system with a rational formula. I agree that degree 2 would also be nice, but to the best of our knowledge, there is no really good horn. There's really no good Kapranov-Hertz theorem here for like Euler characteristic 2 or 3. I think it would be very, very nice. Now again, people in algebraic statistics are very interested. There's some beautiful work recently on the Gaussian case, right? So there's work by Cutley and Cohn and collaborators who extended this from discrete statistical models to Gaussians. And what's behind this is really a differential equation that drives this. So really there's a characterization by PDE that drives this ML degree 1 case. We could hope that something like this exists for like ML degree 2, but we don't know, right? So it's really a differential equation. It's no accident that this person was a differential equations professor.
Yeah, you're not going to get a parameterization in general degree.
Well, if it's 2, maybe you get the formula plus minus square root from high school, right? You can write down plus minus the square root.
That's useful for drawing pictures, but higher degree you get this.
Yeah.
Questions? Any others? Then let's thank Bernd again.